result in unexpected products, which mechanistically include carbocation rearrangements. These can include either alkyl shifts or hydride shifts.
So alkyl shifts can occur when we have different degrees of carbocation stability. So in this halogenation example, we can have a weak pi nucleophile attack a hydrogen to form a secondary carbocation. Because a tertiary carbocation is more stable than a secondary carbocation due to hyperconjugation, this positive charge is going to move to the tertiary.
Dude, stop! What are you doing to my board? Respect the board. Don't draw nonsense on there.
Cause you had a bad day, you're taking one down. You sing a sad song just to turn it around. You say you don't know, you tell me don't lie. You were gonna smile and you go for a ride. You had a bad day, you can't.
Alkyl shifts due to different degrees of carbocation stability can also occur in halogenation. So in this type of reaction, we can see that a weak pi nucleophile can abstract a free hydrogen to form this intermediate with a secondary carbocation on C2. Given the decent amount of ring strain in the cyclobutane, we can form a more stable intermediate by shifting the bond from C6 to C3 to C2, forming a transition state like this to form this intermediate. At which point, our bromine nucleophile can attack our C3 carbocation and form our final product.
Nice job, Connor! Woo!
So this is a 1,2 alkyl shift, and you can tell from the starting material and the products that a shift occurs, because here you start out with 2 carbons in this position, and then in the product you can see that 1 carbon has shifted to a different location. So you start out by protonating this with an H+, and then which adds a hydrogen to make water with a positive charge on the oxygen. Then the water is going to fall off to form this carbocation intermediate, which is then protonated with another H+.
Wait, what are you doing?
Oh yeah, that's not right. This is a secondary carbocation, so this would not happen because tertiary carbocation would be more stable and favored over the secondary, so we would actually want the carbon to shift towards the positive charge, which would then cause a base to come in and deprotonate this hydrogen, which would break the CH bond and cause the electrons to shift and make this bond, completing the elimination reaction.
Oh! I'm going to have to say, goal! They scored. Let's go in 1-0.
I don't really remember.
Becca, go. 3, 2, 1.
Okay, for this carbocation rearrangement, we're doing a 1,2 hydride shift. So to start, this bromine leaves, which forms a carbocation. Next, the hydrogen moves to this carbocation to form a more stable carbocation intermediate. Next, the OAC attacks the carbocation to form this product.